Okay, this is a video on number systems. This isn't all-inclusive. It's just the decimal, binary, octal, and hex. In the PLC class, or in PLCs, there's additional ones that aren't as straightforward, but these are nicely related. So this will take care of this part. When you get into gray code, it's going to look like binary, but it's not binary. And then when you get into binary coded decimal, it's going to have more of a hex form, but it's really a decimal form. And we'll probably go over that a little bit in a different video. Okay, the number systems that we're all used to is what we call the decimal number system, and its powers or its placeholders are based on a power of 10. And the power of 10 is how many symbols we use for each individual position. For instance, in my ones column, 10 to the 0 is 1. In my ones column, I can have anywhere between 0 and 9. And that is true in my tens column, my hundreds column, my 0.1 column, and my 0.01 column. So if I go in there and I add this is 100. This is my tens. These are the placeholders. And we've used these our whole lives, so we sort of know how it goes. We don't think about it in those terms. It is helpful to think about it in those terms, however, when we start changing number systems. So that's our decimal. So if I put in a value of 32, a decimal 32, and I won't get into a decimal number of 32, then I know I have 3 tens and 2 ones. I mean, that's just we interpret it that way naturally. Okay? Now, a binary number system is base 2. So instead of base 10, it's base 2, but the process of the tens power is the same. And notice this G column, I've lined up on my 10 to the my base number to the power of 0, and those are always 1. So 2 to the 0 is 1. 8 to the 0 is going to end up being 1. And 16 to the 0 is going to end up being 1. And it's wanting to remember what I've typed previously, so it's a little bit out there. Okay? Now the nice thing about the binary is 2 to the 1 is 2, 2 to the 2 is 4. 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. So if you're not real good at exponents, all you got to remember is that these just double as you go up. So this is 2. So 1 doubled and became 2, 2 doubled and became 4. 4 doubles and becomes 8, 16, and 32. It also works the same way if you go into decimal numbers. So instead of a 0.1, you are 0.5. And in binary, you either have 0.5 or you don't. So a 0.5. So that's your binary placeholder. Okay? Alrighty. So if I have a binary number, it has to have values of either a 0 or a 1. So 32, and we'll convert that in a minute to binary, means I would have 132 here, and then the rest of these would be zeros. And just like in the decimal number, you don't have to put the decimal point. Just go down to where you would have a decimal point and you're okay. So 32 converts to 1 because it's got 132, no 16s, no 8s, no 4s, no 2s, no 1s. So everything adds up. So we'll do a conversion here in a minute. So if you're given a binary number, you can get to a decimal number by writing it out with its values based on its base, and then adding up the values to get back to the decimal number. If you've got a decimal number and you're converting it to binary, then you write out the binary bases, and then you figure out the biggest one that'll go in there. So I should be able to go all the way up to 63 with what I've got. So let's convert a decimal to binary. So if I've got something reasonable, let's do 7. That'll become apparent in a minute. 7, okay. So I've got 7 decimal, and I want it to be binary. Well, 7 contains a 4, a 2, and a 1. So my 7 decimal becomes 111 binary. In order to not be too confusing, what we have to do is we use subscripts to tell what number systems we've got. So anytime you have a decimal number, you won't have a subscript. But when you have a binary number, you will have a subscript. And the subscript is the base. So 2 is the base. And I looked up the shortcut for this. Let's see if it works. There it is. Shift plus Control plus B will make anything highlighted a subscript. So this tells me that 7, which is decimal, the decimal we're all used to, is equal to 111 in binary. Now, what happens if I want to go from a binary number to a decimal number? So let's think of one. 1, 0. Now everything's subscript. Oh, I can turn it off. Good. 1, 1, 0, 0. How do I know it's binary? It's got a subscript. If it doesn't have the subscript, if it does not have a subscript, even though it's all 1s and 0s, you would assume it's a decimal number. So there has to be a way to distinguish between a decimal number and a binary number if they happen to look the same. And in this case, they do. So what I have to do is go in and put in my 2, and there it is. Now, come off that. Equals. What is that in decimal? So I've got 1, 1, 0, 0. Go back into my spreadsheet. So 0, 0, 1, 1. So I've got 1, 8 and 1, 4. No 2s and no 1s. So 8 plus 4 then is equal to 12. So binary to decimal, you go in and figure out your placeholders. And what I always do is I'll just start. Like if I've got a number like this, I'll say 1's place, 2's place, 4's place, 8's place, and I'll add them up, and there you go. But you gotta be aware of the subscripts. If somebody forgets a subscript, it's a decimal number. Unless it's hex and has a letter in it, in which case you can probably know. Alrighty, so that is binary to decimal, decimal to binary. And these are the common number systems. Now in binary you only have 2. You either have it or you don't. It's a 0 or a 1. It's a binary choice. What you see in PLCs is a lot of times things will be addressed in octal. Octal is base 8, which means there are 7 characters in octal. And we use 0 through 7, which are the same 0 to 7 we use in decimal, but we don't have an 8 and a 9 character in the octal numbering system. In terms of bases, it's the same. So this is the ones column. This would be an eighths column. And this would be 8 squared, or 64. And this would be 1/8, which I believe is 0.125. So 0.125 times whatever you've got in this position. Okay? Now, you can do that, and you can work through it, and you can reason it out. But I like to use a shortcut instead of the base values, because it's an extra step. In binary, when you convert, you're either adding up the value of the placeholder, or you're not. If it's a 1, you added when we did the 1100, we added 8 and 4 because we had an 8 and a 4, but we didn't have a 2 and a 1, so we just added them up. It's an extra level of complexity down here because I can have anywhere between 0 to 7 ones. So if I've got 6 ones, I've got to multiply 6 times 1. If I have a 3 over in this column, I got to do 3 times 8. So then I got to do 3 times 8 plus 6 times 1, and then I've got to add all that up. And it's possible, but it's not necessarily that easy. So the shortcut I always like to use is, if you can get to binary, if you can get from decimal to binary, you can go from binary to octal, and you can go from binary to hex very easily. And that's what I'm saying with these groups of 3s here. Convert binary to octal, I've got a groups of 3. So let's say I've got a binary number, and I'm going to put the binary value of my number in each of these 3 columns. So binary is a 1. Let's say it's a 0, because it's either going to be a 1 or a 0. 1. Oh, I better do 1, and I better do 0. The really neat thing about this is, if I look at these 3 numbers, 1, 1, 0, I can convert them to decimal readily. And if I look at my first 3 columns here, binary, I got 4 plus 2 plus 1. Well, that adds up to 7. So if I go from 0 to 7, I've got 8 possible values, which is exactly what my octal value is. So if these 3 columns were all 1, they would convert to a 7. If they're all zeros, they would convert to a 0. So any combination of 1s and 0s here would come out to be between 0 and 7, which is a valid octal number. So in this case, I've got a 6. And over here, that works out to be a 5. So binary 101-110 converts to 56 octal. Same thing applies with the base. 101-110. I need a base 2, or its decimal, equals 56. Guess what? I now need a base 8 to let you know it's an octal number. Okay? So, if I've got an octal number and I can get it to decimal, I can get from decimal to binary pretty if I've got an octal number and I can get it to binary, I can get from binary to decimal pretty easy. It's a little bit easier. You can probably get an app for your cell phone to do the conversions, but you need to at least know what's happening in the background. So let's try another octal number in this case. 30. Turn off. 36 base 8. You got to be careful with octal numbers because sometimes you got to stay away. You can't use 8 and 9. So you got to stay away from those. Space equals. What is that as a binary number? Well, let's go find out. 36 in octal, and I'm going to convert it to binary. And what I did is I took these 3 here and I combined them. So 36. Now I'm going the other way. So a 6 we know is 1, 1, 0. 1, 1, 0. And a 3 is 0, 1, 1. So we now know that 36 octal is 0, 1, 1, 1, 1, 0 binary. So 0, 1, 1, 1, 1, 0 base 2. And you got to have the base or it ain't a number. Now, some people would do that where they would not write this 0 out here, this leading 0. If you don't see it and you're converting, then you would add a 0 as needed. So sometimes you will see a leading 0, sometimes you won't on a conversion problem. You just add them till you fill out the whole row. That's not that big a deal. All right, now for hex, I have base 16. So it's 1, and now I've got a 16 power. And this would be 1/16, which would be half of the 0.125, and I'm not sure. Well, it's half that, but half of 125 is 62.5, 0.0625. I think that's right. 0.0625. Yeah, that should be right. 0.0625. Now you can have up to 16 of these, or 15 of these I should say, because you could have a 0. So 0 to 15 times this is how you'd convert your decimal. 0 to 15 times this is how you do it. So it's just like up here, and of course it gets very big because what is 16 squared? You might not know it off the top of your head, and I'm not sure what it is. I'd have to multiply it out. Okay, now I need 16 characters. So I can't double. Usually when we go past 9 in decimal, what do? We double. But what we're really doing is we're putting something in the tens power, and then we're counting back to 5. Well, in hex, we can't use 1, 0 because that's really 2 characters. We got to have 1 character. So what happens in a hex system is the A represents decimal 10, B is 11, C is 12, D is 13, etc. 15 is F. So we can do the same thing we did with the octal, except now we're doing groups of 4. So if I want to convert binary to octal, whoops, 1, 0, 1, 1, 1, 1, and then 0, 1, 0, 0. All right, so there's a binary number, base 2, and we want to convert it to octal. So what we're going, hex. So what we got to do is we got to add these up. Now in binary, this is the 8, 4, 2, 1. So 8 plus 2 plus 1 is 11, and 11 is a B. So what I would have here is a B. And then 8, 4, 2, 1, there's only a 4, so this would be 4. So this binary number 10110100 base 2 works out to be B4 in hex. And I'll see if I can remember that. 1 0 1 1 0 1 0 0. Now we got to designate it as a binary number. Well, I don't want to square it. I want to subscript it. Equals, and then we're going to do B4. Now, some people get lazy. If they got a letter in there, they leave it off. I think that's just bad form. Instead of using 16 as the base, usually you will see the H, the lowercase h, as a hex base. So B4 is your hex base. So that's a pretty easy conversion. And then going the other way, I want to convert hex to a binary, so give me a hex number, a 2-digit hex number. So let's be all we can be. So let's do B and E. Yeah, let's be all we can be. So B corresponds to 11, which we just did above. So it's 1 0 1 1 1 0 1 1. E is 14, so that's 8 plus 4 is 12 plus 2 is 14 and no 1. So that would be 1 1 1 0. So that's that conversion. So you just break in each individual character from hex back into 4 binaries. And if you're converting to hex, you take each 4 binaries and you convert it to the hex value. And octal's 3. But in terms of the base power and the way we come up with it, it's the same that you've always done with the 10s. But now we've got 2s, 8s, and 16s. So to finish up, I've got BE16. Get rid of the subscript. BE subscript H, get rid of it, equals 1 0 1 1. I'm cheating because I'm looking up here. 1 1 1 0, and gotta have the base 2. So that's number conversions. Now there is something called binary coded decimal that I alluded to earlier. And what binary coded decimal does is it takes a decimal number and it converts it like the hex. Well, decimal is 0 through 9. So you won't have the hex values in binary coded decimal, but it will take up as much memory as a hex number. It's just a little easier to look at. The other variation you see is something called gray code, and gray code looks like binary because everything's a 1 or a 0. But when you count in binary, what you see is 0, 0, 0, 3 places. If I count in binary, then this is what my first 8 would look like. And I don't think I have to do that. I don't have to go that far. Okay. 0 1 1 1. Oh, come on. 1. There we go. And then 1 0 0. Now, from a decimal standpoint, this is equal to 0 1 2 3 4. So this is decimal, if you will. And then this over here is all binary. Well, binary, what you see is if I go from 0 to 1, only one thing changes. When I go from 1 to 2, this 1 has to change back to a 0, and this 0 has to change to a 1. So there are two changes when I go between the 1 and the 2. And what gray code does is it looks like binary, but as it steps from one position to another, only one digit will change. So I'm 0, 0, 0, 0, 0, 1. That's okay for gray code, and it's okay for binary. But this step from 1 to 2 would not be acceptable in gray code because only one thing can change. So if you look up gray code, you'll see that as the positions change, only one of your binary numbers is changing. Well, it's binary looking, but only one of the values is changing. That's a little easier to resolve if something is rotating, to look for a number to change by one position versus having it change in multiple positions. And look what happened when we went from 3 to 4. This changed to a 0, this changed to a 0, this 0 changed to a 1. So there was 3 changes here. So you wouldn't see that in gray code, but it would look, if you had 3 position gray code, it would look like all these binary numbers. The order would just be jumbled. So that's gray code. And I think I have pretty well covered what I needed to. And I thank you for watching. Oh, let's go back over here. If you are in binary coded decimal, then the subscript is BCD. And that's binary coded decimal. It would be like taking a decimal number and converting it straight to hex. And since you don't have A through F, you don't have to worry about all that. So let's do one. So let's do 23 binary coded decimal. And all this has to be a subscript. And then I'm going to turn it off. Now, what you do when you're going from BCD to decimal, what you do when you go from decimal, I should have done decimal, and this is not right. All right, 23 decimal equals what in binary coded decimal? Get rid of the equal sign. Space. Equals what? Well, now what you do when you convert from decimal to binary coded decimal is you just pretend this is a hex number. So you're going to come up with a 2, which is 0, 0, 1, 0, and a 3, 0, 0, 1, 1. Now, 23 decimal is not this in binary. So if you convert 23 to pure binary, it's not going to come out to be this. So I've got to also go in here and say, oh, what I'm really doing is I'm converting it to BCD. So I've got to have the subscript. And if I'm given a number in BCD and I want to go to decimal, it's a similar process. I've got to look for that BCD, and then I break it up into 4s, and I just take each grouping of 4, I convert it to the number that it corresponds to, and that becomes my decimal. And that's binary coded decimal. But where people get confused is, well, like 36 is not. 7 is actually okay as a binary coded decimal. But 1100, see, you don't have 12. 12 is not a valid thing. So can't do it. What is 23 in binary? Well, I've got a 16s place. So let's start with 23. 23 equals, we know it's decimal. So if I was to convert 23 to binary, I would have a 16s place. Would I have an 8? 16 and 8 is 24, so I wouldn't have an 8. I would have a 4. That gets me to 20, a 1, and a 1. Base 2. And there you go. Okay? That's what I wanted to illustrate. So if I convert 23 to binary coded decimal, I get one thing. If I convert it to straight binary, I would get something else. So that's why the subscript matters. All right, I hope that helps. I hope that encourages you to work with this some. And that's what the reason we do it is because in PLC, your addressing is often in octal or hex. And that has to do with the number of inputs on an input card. For some PLCs, you have 0 through 7, so they're just octal. Some of them are done hex, some of them are like twice the octal. So you can have data in your PLC in an octal or a hex form. And it just has to go with the bits that are actually coming in on an input card. And that's why it's important. And I think there's a question on that at some point. Anyway, I thank you for watching.